Yes, I'm a bit of an outlier, I'm afraid, in this community, but I'm very grateful that you actually scheduled me in the program for this reason, because I'm taking you to a very different environment, looking at wind-blown sand on beaches and also in deserts, of course. And this is a good picture of some streamers over a beach. This is a photo of that. I will move on to the video. I hope this streams through the connection relatively well. I'm sure that most of you are familiar with this sort of visual feature that you might see on beaches during strong winds. And these are called streamers, these longitudinal sort of streaks of wind-blown sand. And it's important for this community, I think, to recognize that, or to understand that this is not a seeded flow. These are sand grains that are jumping and hopping over the surface to a height of about 5 to 10 centimeters. And the sand grains are splashed out of the bed by incoming sand grains. They then get accelerated by the wind flow, and then they bombard back onto the surface, and they splash up other grains. So the sand grains themselves don't move with the airflow itself. They have their own velocities, their own trajectories, their own accelerations. And I've been interested in streamers since I did my PhD, really, and so this is an experimental setup that I used around 2001 to try and measure these streamers in the field together with the wind, to better understand why they form and how they form, so that we can then hopefully improve our physics of the sand transport by setup where I had an array of instruments that are transverse to the wind. And so in this case, you're looking upwind into the wind. You might just about see some streamers on the surface coming towards you. You can see coponemometers for measuring wind speeds at different heights to get shear velocity profiles. And then these little black tubes, this is a span-wise array of little, essentially microphones that measure the impact of sand grains. From that research, we really developed a much better hypothesis of how streams are formed, and that we're thinking that in the context of eddies and large coherent flow structures that impinge on the bed and essentially rake up sand grains as the eddy is sort of raking over the bed. It sort of throws up sand grains in the air that then flow as these streamers in the general flow field. So that's sort of our idea. Now, obviously, at the time already, I had some pretty coarse-grained video imagery, video footage of streamers, and this is in 2001, as you can see. And I'm sure I wasn't the only one at but this is still relatively early days, pretty grainy footage. So I then developed a project to try and film these streamers over the surface a bit better. Now, this was in 2006. We're working in silos. Unfortunately, at this point, I was completely unaware of anything to do with LSPIV. I'm ashamed to say I'd never heard of Fujita before that. I did know about PIV, so I thought of this as a sort of PIV of patterns instead of tracking individual particles, trying to track patterns. And so at the time, we basically developed our own LSPIV algorithm using direct cross correlations in a sort of telescoping, a nested sort of sequencing. That work then we submitted to a journal in 2008, but the submission got completely slaughtered by my peers because they basically had never heard of this stuff before. It was all completely novel, and I think half of it wasn't really understood. Eventually, we turned it around. About 10 years later, I turned it around and got it eventually published. But I just kind of want to take you through that work. We initially did some lab testing to try and get some footage of sand grains, in this case falling down. So we had a little scaffold tower, and basically poured sand grains down in front of a black cardboard background. And so I've got some footage here that hopefully will come through. I think you can just about see these little clouds of sand grains falling through, and those were to mimic the streamers, really. And then we filmed that using a video camera. And then we developed from that, we developed this sort of LSPIV approach, looking at two consecutive frames here, left and right, subtracting the black background from it to just focus on the falling sand grains. And then measuring the displacement, of course, from one frame to the next. And so we can then look at the vectors that come out of that at different scales. And that was pretty successful in actually measuring the fall velocity of these sand grains and even the acceleration of those grains from the top of the image to the bottom of the image as they were.
Oops, I don't know if Andreas's internet connection has dropped out or if he's pressed a button.
I think he's disappeared from the meeting. I can't see him in the participant list. Shall we give him a minute or so to see if he rejoins? And if he doesn't, perhaps we should move to the next presenter if he's not back quite rapidly.
Yeah, I think that's a good idea.
Who's next?
It's Erica.
Erica, are you ready, Erica, if we don't get Andreas back?
Yes.
Excellent.
This was around about your scheduled talk time anyway, so unfortunately we're running late.
Yeah. It was an interesting topic, application of the method to sand. I think it's nice to bring in, you know, talks from different disciplines that can sometimes bring new insights into things. So, so it's a shame we've lost him. But what do you think, Rob? I don't see him re-entering the room because we can always ask him to.
He's just requested to be.
He's back. Here he is. Andreas, are you there?
Yeah, I don't know what happened. Yeah, when did I drop out?
You've just shown us the clips with the 96 pixel and the 98 millimeters and the 58 millimeter pixels, I think.
Yeah, okay, so that was this one probably.
Forward one maybe.
Yeah, exactly. So I was here, wasn't I?
Yeah, I think so.
Yeah. Okay, so here we've got the two frames on the left. On the right, you see the background subtracted, and you can make out this streamer here moving from right to left. You can see the displacement, and so we could track that using the PICs, you know, the direct cross correlation. So here you see the overlaying vectors on the source image, and then on the left-hand side are two different spatial scales. And on the right-hand side, you can see the cross-correlation coefficients that are associated with those vectors. And on particularly the higher resolution scale, you see that the highest correlations are actually associated with the edges of the streamers, which makes sense because those are the clearest differentiations in the pattern, really. So that's sort of what we developed. That then allowed us to look at the time series of advection speeds of these streamers as they moved across that surface. As you can see, it actually varies over time quite significantly. Here in the blue, in the dark blue is the average over the whole frame, and then the banding around it is the distribution of the velocities across each frame. And as you can see, it's quite varied over time. We could also track, obviously, the directions of these different vectors. Now, as you might remember that we were taking these images and we could stitch them all together in a sort of continuous sequence map, sort of assuming a Taylor hypothesis approach, which then allowed us to really kind of map out longer structures beyond the confines of just a single frame. that original experiment in 2006 was only using a video camera. And of course, we want to now match it up with the wind and also direct measurements of sand transport. So this is sort of a new version of this experiment just last year in September on the same beach, in fact, but now using a GoPro Hero camera, pretty cheap, but a much higher resolution, of course, and that's the attraction here. And then also using a sonic anemometer to measure wind speeds, and I've got a little zoom in here of the instrumentation. Here in blue, these little forks are laser sensors that can measure the sand grains blowing through the laser light, so we can actually measure transport rates directly. That's only a very recent data collection, so I'm still working on the imagery and that. This is the view from the video camera itself. Because we're working in air, it's relatively easy to then very quickly lay down a checkerboard pattern to provide ground control points, to convert the oblique imagery to a plan view, and also convert it to grayscale in this case. So we're going from this kind of footage. I'll show you a little bit of video imagery. This is the original video imagery from the GoPro Hero. Let me mute that for you. You can just about see these smudges moving through in the original video there. And then we move that to, this is the converted plan view imagery in a grayscale. And you might hardly see any changes. You might just about see slightly brighter patches moving through from right to left. So the signal originally in the grayscale seems very faint, but eventually I managed to come up with some background subtraction techniques, a bit of a dark art, I'm afraid, which then allowed me to really extract the actual moving sand patterns out of that imagery here. So that's what we see here, I think, if I'm still there. Yes. So that's where I'm largely at right now. I've been able to look at the advection of the streamer patterns on a whole frame, on the scale of the whole frame. And that has already shown me some variable advection speeds here between sort of 2 to about 5 meters per second. We can then also do histograms of that to get some idea of the distribution of advection speeds over time. And I've also started now matching up the measurements from the laser sensors to the pixels in the video imagery. And so on the top, you see pixel intensities from the footage here in blue. And on the bottom in red here, you see measurements from the laser sensors of sand transport rate. And as you can see, there is a relatively decent correspondence. Obviously, we need to do a lot more work on this. So some very final thoughts. I think some previous presentations on Tuesday and perhaps yesterday already mentioned this idea. It'd be great to have some sort of repository of testing footage, and I'll be really keen on something like that to try and see how the algorithm that we sort of developed in our own naivety, I'd love to try and test it on some well-known hydraulic footage, perhaps, to see how it compares. And another big challenge that we're facing is that once we actually have all these measurements out of the LSPIV, we're looking at essentially dynamic vector fields, and it's still a bit of a challenge to think about how we can really analyze those in a more rigorous sort of quantitative way rather than just kind of visually, subjectively identifying interesting features. So I'll leave it there. Sorry for that interruption, but I hope that this has been able to entertain you a little bit. Thank you.
Thanks, Andreas.